Hi, this is Math 2510, and this video is over chapter 2.6, and we're going to look at continuity, which is really just a fancy way of saying we're going to look at when functions are continuous and what makes a function not continuous. Right, so the function is continuous at a if the limit of the function as x goes to a of f of x equals f of a. It's a simple definition, but it does involve three major parts. First, f of a is defined. That is, a is in the domain of f of x, or your function. Okay, so one thing you want to do is find the domain of f of x and look at points that are not in the domain. Not in the domain. That is a huge indicator that those points have discontinuities. Next one is that the limit as f of x as x goes to a exists. The is threw me off there. It shouldn't be. It has to exist. So that has to be a limit. Okay, that limit could be L, some value, could be infinity or negative infinity. But there has to be a limit. And then on top of that, the two are equal. So limit as x goes to a f of x equals f of a. Alright, so if these three conditions aren't satisfied, we say that f is discontinuous. At a, if f is not continuous at a. Okay. So another way to kind of get a meaning of these, f of a is defined means there are no breaks in the graph at point A. The limit being defined, or a limit existing, means that the limit of f of x from the left equals the limit of f of x from the right. And then the last one, the fact that the limit has to equal f of a means that the value of f equals the limit of f, or f of x, at a. Okay, so again, the first criteria means there can't be a break in the graph. This rules out vertical asymptotes. Okay, so vertical asymptotes means there are points discontinuity. Think of discontinuity. If you can't draw the graph in a straight line without picking up your pencil, then it's not continuous. We call this an infinite discontinuity. The second criteria is that there can't be a jump. at A. Second criteria meaning that the limit is defined, there has to be a limit for it. Or there's a jump discontinuity. We'll see as we go through these which ones are jump discontinuities, which ones are actual other infinite discontinuities. There's a couple more. Third criteria means that the graph can't have a hole at x equals a. So you don't get close to a and expect one value, and then when you reach a, you end up with a different value. We call this a removable discontinuity. Because we could redefine f at a as just a single number. Alright, so let's look through some examples. First, f of x equaling 3 over x plus 5. So x cannot equal 5. 5 is not in the domain, so that's going to be a point of discontinuity. If we were to look at this graph, we see an asymptote. Right here at, not zoomed in, so there's, but right here at 5, there's an asymptote. Right. So we have a vertical asymptote. At x equals 5. I'm sorry, that's at negative 5. Equals negative 5. And so we have an infinite discontinuity. We call it infinite because, both sides of the graph are going to infinity, or negative infinity in that other case. So the next one, x squared minus 1 over x minus 1, we can factor this. And when we factor it, we get x plus 1. The x minus 1s cancel out. Right. So, 1, we can see that in the domain x cannot equal 1, that you would end up with a discontinuity. It's not in the domain. Now, what type? It's not an asymptote there, so it's not infinite discontinuity. If we graph it, we end up seeing that it's just a line. And it's a line going through, and it looks like it goes through even at point 1. Okay, well, let's see what happens when we plot point 1. So I'm going to actually make that f of x so I can refer to it. And we plot 1 f of x. I'm not going to be able to do it that way. Do it this way. Do a table. X of x. And 1, you get undefined. So even though it looks in the graph like those, it goes right through it, it's really a hole there. Okay, so you have a hole. And we can use the function itself at f of 1. We use an x plus 1, you get 1 plus 1, which is 2. So at point 1, 2, you have a hole. This open circle. Right. So you do have a hole there. And so we call this a removable discontinuity at x equals 1. Bring up. In the third one, we are looking at a piecewise function. And so we're going to be concerned with what happens at 2. Okay. Each of these graphs, if you don't worry about the restricted domain, each of those graphs do have domains that are real numbers. But we have to look at, see what happens at 2. So f of 2, 3 minus 2, will be 1. F of 2 for 2 over 2 plus 2, 1, is going to be 2. Okay. This creates a jump discontinuity. The graph would jump from one spot to another spot where you have to pick up your pencil, draw it. Okay. A lot of times this happens with piecewise functions. We can graph it to show it. Right, now we're going to have to restrict the domain. So it only shows the parts we want. That'll be x is less than or equal to 2. And this one will be x is greater than 2. Okay, so we see there's a jump between where the red line ends and the blue line begins. Okay, we can plug in the point. Let's do a table x, x, your one more f of x. And we can plug in, let's do 1. The second column is undefined because that's not part of that domain. This is a restricted domains, so 1 falls on the red line graph. Do 2, we see 2 falls on the red line. I see what happened. Don't worry about these colors. It's no change them. So, I see. These are the points. No, I want them both. Okay. So 2 falls on the red graph, so it's in the first column. 3 will fall on the blue graph. Okay. The point, we have the point that's included. The point that's not included is our 2, 2. That's an open point. And it's not included because that part of the graph is not in the actual domain of f of x. But we see there is the jump between the two. All right. That leads us into talking about endpoints. Given a function y equals f of x, It's continuous at the left endpoint if f of x is continuous from the right. This is, you can think of it as the positive side. So I'm just going to draw a quick graph. Endpoint. This is your left endpoint since it's left of the graph. As long as we're continuous coming in from the right, which is the positive side, it's continuous. It's continuous from the right endpoint if f of x is continuous from the left negative side. So this point coming in from the left negative side has to be continuous going into the right endpoint. Right, so we're going to look at this graph. We're going to look at the different points where f is not continuous. We see a jump. We see a removable discontinuity. And there's no other, no vertical asymptote. So there's none of that. We see going into the endpoints, this is continuous. This one's continuous. And this one's continuous. Right, the endpoint at 1, x equals 1 to 1, 0. This endpoint's not even included, so we don't have to worry about whether it's continuous or not. The going into a hole, we also don't count that as an endpoint. So the places of discontinuity for this graph, f of x is discontinuous at x equals 1 because of a jump, at x equals 2 of a hole or removable discontinuity. For the jump, the limit as x goes into 1 from the negative side does not equal the limit as x goes into 1 from the positive side. This one equals, the negative side equals 0, from the positive side equals 1. So those limits are not equal. That's why a jump does not have a continuity. For the removable one, the limit as x goes to 2 of f of x equals 1, but f of 2 will equal 2. So the limit as x goes to 2 f of x does not equal f of a. That's why those are discontinuous. Alright, so a function is continuous on an interval if it is continuous everywhere, at every number in that interval. If f is defined only on one side of an endpoint of the interval, we understand continuous at the endpoint to mean continuous from the left or from the right, depending on if it's the left side or the right side endpoint. A continuous function is one that is continuous at every point in its domain. So that means that continuous functions include polynomials, radicals, even, I write this down lower, even rational. They're continuous everywhere in the domain. Vertical asymptote is not in their domain. So there is a point of discontinuity on the graph, but not for the function. And then also trig functions. And I will write these later too as well. Right, so we can use the operations of functions like we would for composites or combining functions in much the same way. F of g, if f and g are continuous at a and c, a for f, c for g, then the following functions are also continuous at a. F plus g will be continuous. F minus g will be continuous. C is a constant, so C times F is continuous. F times G is continuous. And F divided by G is continuous with the exception that G of A cannot equal 0. So sine, which looks like this, is a continuous function. X cubed is a continuous function. So sine of x plus x cubed is continuous. X cubed plus sine of x is continuous. Sine of x minus x cubed is continuous. X cubed minus sine x is continuous. Some number c times x cubed, or c times sine of x, they're continuous. X cubed sine x, or sine x cubed, they are continuous. And then sine x over x cubed is continuous except at x equals 0. And x cubed over sine x is continuous except when x equals numbers of pi over 2's. Odd numbers of pi over 2, I should say that. So 2n minus 1 pi over 2. Every 90 degrees, basically. Every pi over 2, 3 pi over 2, so on. Any polynomial is continuous everywhere. That is, it's continuous on all real numbers. Any rational function is continuous everywhere it's defined, so anywhere in its domain. Okay, so there may be points again of discontinuity. But again, polynomials, they're one of the better ones because you don't have to worry about any discontinuities, functions, or radicals. Rational, trig. Exponentials, logs, also continuous on their domain. So we want to look at when intervals are continuous. X over 9, rational function, but the domain is all real numbers, infinity to infinity. So that's what it's continuous on. The x squared minus ax minus 20 over x squared minus 4. We'll find the domain is negative infinity to 2, negative 2, negative 2 to 2, and 2 to infinity. Okay. 2 and negative 2 cause that to be to cause a discontinuity there. But in the domains, there's 3 regions where it's continuous. Right. If we look at the numerator, that actually can factor. I'm going to write it down here below. So this can factor into x. Let's see here, and then 2. So negative 10, x plus 2. And then the bottom factors into x plus 2, x minus 2. So the x plus 2 cancel. You have a hole there. So you have a hole at x equals negative 2. So you have a removable discontinuity. At x equals 2, you have vertical asymptote. So no matter how we define f of 2, it's still going to be discontinued. There'll still be a discontinuity there. So this represents an infinite discontinuity. I'll write this down here. Remove discontinuity. We look at the third one, x squared plus 3. There's no way to set this equal 0. It's all real numbers again. No discontinuity there. All right, so we want to find the numbers at which this function, piecewise function, is continuous. At which of these numbers is f continuous from the right, from the left, or neither? So what we're going to do, we're going to graph this. Run Desmos. It's just a piecewise function. I'll use, so to build it from here. So that's equal to 1. X is less than 0. Then it's absolute value of x. Absolute value, it's a function here somewhere. Oh, I see it. It's over here. Absolute value of x. And this would be from 0 less than equal to x less than 1. Then we'll do one more. We'll call this, let's call this g of x, just so we can identify the pieces. We'll set that equal to x minus 1 squared plus 1. So this will be g of x. All right, so we can look at different points on this. So we can look at negative 1. We see it's defined here in f of x as 1. We could look at, oh, I didn't do that. I gotta finish this up. X greater than or equal to, wait, Yeah. We can do, let's see, x equals 1 as well. We see it's the last one. Actually, I want to do a point between them. So let's do 1/2. Then we'll do. And so we see what these points are. Now, the points we have to be concerned with are going to be x equals 0 and x equals 1, because that's where you have the breaks, right? The breaks in the pieces of the function. So x equals 0 and x equals 1 is what we want to look at. Up to that point, it's continuous for sure between -infinity and 0. We just have to figure out if 0 is included. Well, we can see the graph between the red line and the blue line, there's a jump. Okay? The limit as x goes to 0 of our function f of x from the left side is equal to 1. The limit as x goes to 0 from the positive side, that's equal to 0. So on here, we got 1. Okay, like this. So these limits not the same. And again, this leads to a jump discontinuity. Now we look at x equals 1. Well, the limits there are both the same. Limit as x goes to 1 from the negative side of f of x equals 1, which also is the same as the limit as x goes to 1 from the positive side. We also can look at the function value f of 1 equals 1 minus 1 squared plus 1. That's 0, so that equals 1. So the limit as x goes to 1 of our function equals 1, which equals f of 1. So 1 here at x equals 1, you have a continuity. So we can write now points of continuity as -infinity to 0, 0 to infinity. 0 is the only point that's not continuous. We're looking at the function f of x here, x squared minus 1, when x is less than 3, and 2kx when x is greater than or equal to 3. We'll find the value for k so that the function is continuous for these pieces. So first, you want to plug in 3 and look at the borderline 3, because that's going to be the issue. 3 squared minus 1, and it has to be equal to 2kx. in order to have continuous there. But at those points of 3, these two have to be the same. Where did that come from? There you go. And must have just hit it. Right, so we can, that x should also be a 3. So we can solve this for k. So we get 9 minus 1 equals 6k. 8 equals 6k, so k equals 8 over 6, or 4 over 3. So in this case, 3 squared minus 1 will equal 8. 2 times 4 over 3 times 3 will equal 8. So f of 3 equals 8. The limit as x goes to 3 of 2x minus 1 equals the limit as x goes to 3 of 2 times 4 thirds x. They will be the same then. So now k has to equal 4 thirds. That's happened. Alright, so if f is continuous at b and the limit as x goes to a of g of x equals b, then the limit as x goes to a of f of g of x equals f of b. In other words, the limit as x goes to a of f of g of x is the same thing as f of the limit as x goes to a of g of x. Okay. So the theorem is saying that the limit symbol can be moved into a function if the function is continuous and the limit exists. In other words, the order of these two symbols can be switched. So let's actually apply this. We have the limit as x goes to 2, x to the fourth minus 5x cubed plus x squared minus 7. It is a polynomial and continuous everywhere, as it is a polynomial. So the limit as x goes to 2 can be found of a function, let me write in the function, can be found by 2 to the fourth minus 5 to the third plus 2 squared minus 7. 16 minus 40 plus 4 minus 7 is 8.7. You can take the limit of the function, plug it into the function itself, plug it into the limit, I should say. In this case, we have limit as x goes to 0 of square root of x squared minus 3x plus 2. We can factor this. Square root of x minus 2 is x minus 1. And we can look, and on this graph, we'll have points 1 and 2 where this is going to be 0 and positive less than 1 greater than 2. And you can just plug in a value. Plug in 0.5, you see that you have a negative. and a negative, which goes to your positive. Plug in 1.5, you have a negative and a positive, which gives you a negative. Plug in 3, you have two positives, gives you a positive. So the domain is here and here. Our domain is from negative infinity to 1, including 1, and 2 to infinity. Now, x is going to 0. 0 is here. We're only concerned about the left part, since x is going to 0. And so this function is a radical and defined from negative infinity to 1. So it's continuous from negative infinity to 1. So the limit as x goes to 0, square root of x squared minus 3x plus 2 equals square root 0 squared minus 3 times 0 plus 2, which is going to be equal to square root. All right, so if g is continuous at a and f is continuous at g of a, then composites of f composite with g given by f composite g of x is equal to f of g of x is continuous at a. One more problem with this. Composites is an important method for constructing continuous functions. So if we're looking at f of x equals sine of x, it's continuous for all x. G of x equals x to the fourth minus 7x squared plus x plus 1 is continuous for all x. Then f composite with g of x is continuous for all x. So that means sine of x to the fourth minus 7x squared plus x plus 1, and sine of x to the fourth minus 7 times sine x squared plus sine x plus 1 continuous. All right, the last thing in this section is the intermediate value theorem. Here, continuous functions possess the intermediate value property. Basically, what this is if we have a function, let's call this f of x. This will be f of x. And we're going to call the next function, actually, it won't be a function. We'll call this line here n. We're going to look at point C, which is where these cross. So suppose f is continuous on the closed interval AB. AB is going to be from here, the x origin, to up here. So it's beyond C. And let n be a number between f of A and f of B. So here's f of A, up here will be f of B. Okay. So n is a point in between. And there exists a number C in A and B or between A and B, where f of c equals n, which is this point. F of c equals n. In other words, what we're saying is if all functions continuous, then to cross a specific line, it must go through it. And so there must be a point that exists through it. There's no way of jumping from this side here to this side here without having that point here. You have to cross that point if it's continuous. Okay? We use this in algebra before to kind of show where an x-intercept is, using the line of x equals 0 as a place of the number n in a sense. And so, in a sense, it's because it's continuous that a point's going to be defined there. You just may not know exactly where it is. You can think of it as if you throw your house keys into a cornfield, you know they're out there, you just don't know where they are. And finding them may be a lot harder. So the intermediate volume theorem says there is a number c such that f of c equals k, k being the y value here, and say n. But it doesn't tell you how to find it. It doesn't tell you exactly where it is, or how many there are for that matter. Okay, so there could be more values of c that have that point. And we can make that happen just by looking at it like this. Function that looks like this. Now we just added values and more c values in a sense. Alright, so let's do one last problem. Show and explain why x to the fifth plus 7x cubed plus 7x plus 1 equals 0. Has at least one solution between -1 and 0. So we plug in -1. And we find out what that value is. This is when x equals -1. We get a -1. We get -7. We get -6 plus 1. We get -13. I don't know, that should be a -6. I subtracted for some reason. It's negative, that's the important part. Now we're going to look at x equals 0, 0 to the fifth, plus 7 times 0 cubed, plus 7 times 0. All of these are going to end up being 0 anyway, so you get 1. So because f of 0 is positive, positive and it's 1, and f of -1 is negative, it ends up being 14. Oh, -1, sorry, 1 away. Right, so because of that, and because this function is a polynomial, which means it's continuous, so function polynomial and continuous, then to make a line through here, it has to have a point in between. That point is C. Now, it could have multiple points. Maybe it does. Oops. Maybe it does something like this. but there has to be at least one. Alright, so that is it for this chapter, and I will see you in chapter 3.